You think you know what the speed of light means? 300,000 kilometers per second. The ultimate speed limit of the universe. Nothing can go faster. No signal. No force. No information. That rule is so deeply built into modern physics that everything depends on it. Without it, cause and effect would collapse. Time would lose meaning. Reality would stop making sense. And yet, in 1935, one man claimed that quantum physics breaks this rule. That man was Albert Einstein. At the time, many physicists thought he was finished. They believed he was an aging genius who could not accept new ideas. Quantum mechanics was strange, probabilistic, and deeply unsettling. Einstein did not like it. So when he criticized it, people assumed he was just being stubborn. They were wrong. Einstein was not confused, he was worried. Because he had found something that looked impossible. 30 years earlier, Einstein had already transformed physics. He had shown that time and space are flexible, that observers moving at different speeds experience reality differently, that nothing can outrun light. And he had fixed gravity by turning it into curved space-time, where effects spread gradually instead of instantly. Locality. That was the key. Causes must travel through space. Nothing can act instantly at a distance. Without this rule, physics falls apart. Einstein believed it was sacred. Then quantum mechanics arrived, and it broke it. To understand why, imagine something simple. You fire a single electron through a narrow opening toward a screen. According to quantum mechanics, the electron is not just a tiny particle. It is also described by a wave that spreads out in space. This wave represents probabilities. Where the wave is strong, the electron is likely to appear. Where it is weak, it is unlikely. When the electron hits the screen, you see a tiny dot at one place. Only one, not many. But before the measurement, the wave was everywhere. So what happened? Quantum theory says the wave function collapsed instantly, everywhere at once. The moment you detected the electron here, the probability of finding it anywhere else dropped to zero. No delay, no travel time, no signal. Just immediate change across space. Einstein saw the problem immediately. If this collapse is real, then something is happening faster than light. Information is spreading instantly. That violates relativity. That violates causality. That violates everything he had built. He called it spooky action at a distance. And he refused to accept it. At a famous conference in 1927, Einstein challenged the founders of quantum theory. He presented this argument in front of the world's greatest physicists. He asked a simple question. How does the wave know where to collapse? How does one measurement affect distant space instantly? No one had a clear answer. The most influential physicist in the room was Niels Bohr. Bohr believed that quantum mechanics did not describe reality itself. It only described what we can measure. According to him, asking what an electron is doing when you're not looking is meaningless. Physics, he said, is about predictions, not about hidden truths. If the math works, that's enough. This became known as the Copenhagen interpretation, and it dominated physics. But Einstein hated it. He believed reality must exist independently of observation. He believed particles had definite properties, even when no one was watching. To him, the idea that reality depends on measurement felt like surrender, like giving up on understanding. He called it a tranquilizing philosophy, a way to stop asking hard questions. So he kept fighting. For years, he searched for a deeper theory, one that would restore locality, one that would explain quantum effects without instant action. And in 1935, he made his boldest move. Together with Boris Podolsky and Nathan Rosen, he published a paper that would become famous as the EPR paper. Its goal was simple: to prove that quantum mechanics was incomplete, to show that something deeper had to exist underneath, something local, something realistic, something Einstein could accept. And to do that, he introduced one of the strangest ideas in all of science: entanglement. Two particles, one state, no separation. To understand what Einstein was really trying to show, imagine a single event in deep space, a burst of energy, a flash of light. A high-energy photon suddenly transforms into two particles, an electron and a positron, one negative, one positive, perfectly balanced. They fly apart in opposite directions. But something invisible ties them together: spin. Every electron has a property called spin. It is not literal rotation. It is a quantum characteristic, a kind of built-in angular momentum. Spin can point in different directions, up or down, plus or minus. But in this case, the total spin must be zero. So if the electron ends up spin up, the positron must be spin down. If one is left, the other is right. They are linked. Before anyone measures them, quantum mechanics says they are not in one state or the other. They are in all possible states at once. A superposition. Both up and down, both left and right, both yes and no, at the same time. Only when someone measures them does reality choose. Now imagine separating these two particles. Send the electron to one laboratory. Send the positron to another. Miles apart. Maybe continents apart. Maybe light years apart. Distance does not matter. The connection remains. Now each laboratory prepares a device to measure spin. A Stern-Gerlach machine. A strange magnet that splits particles based on their spin. If the particle is spin up, it goes one way. If it is spin down, it goes the other. No ambiguity. No ambiguity. So the experiment begins. In Lab A, a scientist measures the electron. It goes up, plus. Instantly, without delay, the positron in Lab B must be down, minus, not later, not after a signal, immediately. Because if it weren't, conservation of spin would be violated. Nature would break its own rules, and that never happens. So the moment one particle is measured, the other is fixed, no matter how far away. This is entanglement. Two separate objects behaving like one system. Now comes Einstein's question. How does the second particle know? No light signal can travel that fast. No radio wave, no particle, no force, nothing. Yet the correlation is perfect every time. It looks like information travels instantly, faster than light. Einstein and his colleagues used a simple analogy. Imagine each particle carries an envelope. Inside the envelope is the answer, plus or minus. Before measurement, both answers exist. When you open one envelope and see plus, the other envelope must instantly contain minus. But how? Either the envelopes already had answers from the beginning, or one envelope somehow sends a message to the other. If the answers were fixed in advance, then quantum mechanics is incomplete. There must be hidden variables. Secret information built into particles from birth. If the answers are not fixed, then information must travel faster than light. Both options are shocking. Einstein preferred the first. Hidden variables. A deeper layer of reality. A local theory. No spooky action. No instant influence. Just ignorance. We don't know the answers, but they exist. Quantum mechanics, he believed, was just a statistical shortcut. Not the full story. This seemed reasonable. In everyday life, randomness usually means lack of information. If you flip a coin, the result feels random. But in principle, if you knew every detail, you could predict it. Einstein believed quantum randomness was the same. Apparent chance hiding deeper certainty. Bohr disagreed. He believed the randomness was real. There were no hidden answers. Reality itself was probabilistic. Before measurement, there was no fact of the matter, only possibilities. The envelope was empty until you opened it, and opening one created the content of the other, instantly, across space. This disagreement was not about math. Both sides used the same equations. It was about what those equations meant. Was reality definite but unknown, or indefinite until observed? Einstein thought the first. Bohr defended the second. And for decades, there was no way to decide. No experiment could distinguish between them. Both interpretations made the same predictions. So most physicists sided with Bohr, not because he had proven Einstein wrong, but because his view worked. It produced results. It built technology. It solved problems. Einstein's objections were treated as philosophical, interesting, but irrelevant. And slowly, his position faded. He died believing quantum mechanics was unfinished. That someday, someone would find the deeper theory. That locality would be restored. That common sense would return. But he never lived to see what happened next, because 30 years later, someone found a way to test him, and the universe answered. For almost 30 years, the argument between Einstein and Bohr remained unresolved. Two visions of reality. One said the universe is complete, local, and deterministic, even if we don't yet understand it. The other said the universe is fundamentally probabilistic, non-local, and shaped by observation. Both matched every experiment. Both predicted the same outcomes. There was no way to tell which was right, so physics moved on. New theories were built, new technologies emerged, new generations were trained, and Einstein's doubts slowly became historical footnotes, until a quiet physicist named John Bell changed everything. In 1964, working at CERN, Bell noticed something that almost everyone else had missed. Einstein's argument was not just philosophical. It could be turned into mathematics, and mathematics could be tested. Bell realized that any local hidden variable theory must obey certain statistical limits. No matter how complicated the hidden mechanisms were, if information could not travel faster than light, the correlations between entangled particles could only be so strong. There was a ceiling, a boundary, a line that could not be crossed. He wrote it down as an equation, now called Bell's inequality. Quantum mechanics predicted something shocking. It said nature violates that inequality. It said entangled particles should be more strongly correlated than any local theory allows. In other words, if quantum mechanics was right, Einstein had to be wrong. Not philosophically, experimentally. This was revolutionary. For the first time, there was a way to decide, not by debate, by measurement. If experiments respected Bell's limit, hidden variables existed. If they broke it, non-locality was real. For years, the technology was not good enough. Measuring single particles with precision is difficult. Keeping systems isolated from noise is difficult. Synchronizing distant detectors is difficult. Everything had to work perfectly. Then, in the 1970s and 1980s, it became possible. Teams began building Bell test experiments. Pairs of entangled photons were created, sent in opposite directions, measured independently, thousands of times, millions of times. The results were clear. Again and again, Bell's inequality was violated. Nature crossed the line. Quantum mechanics was right. No local hidden variable theory could explain the data. The universe was non-local. Information was not stored in advance. The outcomes were not predetermined. Measurement created reality. And correlations appeared instantly, across space, across distance, across distant limits. Einstein's hope for deeper local theory collapsed. There was no escape, no loophole, no hidden clockwork underneath. This was not ignorance. It was fundamental. Later experiments closed every remaining gap. They eliminated timing loopholes, detection loopholes, communication loopholes. By the 2010s, loophole-free Bell tests had been performed using satellites, using fiber optics, using distant laboratories. They all agreed. Reality is entangled. The universe does not respect classical locality. Something happens outside normal space-time connections. And yet, relativity survives. No usable signal travels faster than light. You cannot use entanglement to send messages. You cannot transmit information. The randomness remains. Only correlations are instantaneous. This is the strangest part. The universe violates locality without violating causality. It connects distant events without allowing control. It links outcomes without enabling communication. It is non-local but not exploitable, connected but constrained. This delicate balance is what makes reality consistent and deeply weird. Now, physicists had a problem. If non-locality is real, what does it mean? How does the universe do this? Where is the connection? What is being exchanged? No one knows. Quantum theory describes it perfectly, but it does not explain it. It gives probabilities, not mechanisms. So new interpretations emerged. Some physicists accepted collapse as fundamental. Reality jumps, information updates. That's it. Others propose that all outcomes happen. Every measurement splits the universe, many worlds. In one branch, the electron is up. In another, it is down. Entanglement is just correlation between branches. No signal, no collapse. Just parallel realities. Still others propose pilot waves, hidden guiding fields, non-local but deterministic. Strange, but consistent. None of these interpretations change predictions. They all fit the data. They differ only in meaning. And that means physics returned to philosophy. After proving Einstein wrong, it had to ask a deeper question. What is reality? Is it one world or many? Is randomness real or apparent? Is the wave function physical or abstract? Is collapse real or illusory? We don't know. What we know is this. Entanglement is not rare. It is everywhere. In atoms, in molecules, in solids, in biological systems, in computers. Every object around you is held together by entangled particles. Decoherence hides it. Interaction with the environment destroys fragile quantum links. But at the foundation, everything is connected. The classical world is built on quantum entanglement. We just don't see it until we isolate it, until we control it, until we make it visible. And now humans are learning to do exactly that. Quantum computers use entanglement. Quantum cryptography relies on it. Quantum teleportation exploits it. The strangest feature of reality has become a tool. What Einstein saw as a flaw has become a resource. The universe's weirdness is now engineering material. And that brings us to the final question. If reality is non-local, if outcomes are not predetermined, if observation matters, then what does that say about us? About knowledge, about existence? By the time physicists accepted that entanglement was real, something profound had changed. It was no longer possible to pretend that reality was simple. It was no longer possible to imagine the universe as a collection of independent objects moving through space, obeying clear rules like clockwork. That picture was gone. In its place stood something stranger. A universe made of relationships, connections, correlations, possibilities. A universe where distance does not mean separation. Where two particles can be light years apart and still behave as one. Where information is not stored in objects, but in patterns linking them. This is not poetry. It is measurement. It is what experiments have shown. Again, and again, and again. And this forces a rethinking of what it means for something to exist. In classical physics, an object has properties whether you look or not. A ball has a position. A planet has a velocity. A clock has a time. Quantum physics says that at the deepest level, this is not true. Before measurement, many properties do not exist as facts. They exist as probabilities, as potential, as mathematical possibilities. Reality is not a list of answers. It is a cloud of options. An observation selects one. This does not mean that consciousness creates reality. It means interaction creates reality. Measurement is just a special kind of interaction. When a particle meets a detector, when light hits a screen, when an atom collides with another atom, information becomes definite. Before that, it is distributed. This is what wave functions represent, not ignorance, possibility. Entanglement takes this idea further. It says that possibilities can be shared. Two particles can exist in a combined state that cannot be separated. Their identities overlap. Their futures are linked. You cannot fully describe one without the other, even when space separates them. This is why the classical idea of parts breaks down. At the quantum level, the universe is not made of independent pieces. It is made of inseparable systems. Wholes first, parts second. And this is where interpretation matters. Some physicists believe that when you measure, the wave function really collapses. One possibility becomes real. All others disappear. Reality jumps. Others believe nothing collapses. All possibilities continue. The universe splits. Every outcome exists in its own branch. You experience only one. Still others believe in hidden structures guiding outcomes. Non-local but deterministic. All mathematically consistent. All experimentally identical. Which is right? We do not know. And that uncertainty is not a weakness. It is honesty. Physics tells you what happens, not what it means. Meaning is something humans add afterward. What is certain is that entanglement is not rare or special. It is the default. Every atom in your body was once entangled with atoms and stars. Every electron in your brain shares history with distant galaxies. The early universe was a single quantum system. Everything today emerged from that unity. Cosmic entanglement is the background of existence. Most of it is hidden by decoherence. Interactions with the environment destroy fragile correlations. Quantum systems become classical. Possibilities collapse into facts. The world becomes solid, predictable, stable. That is why chairs don't tunnel through floors. That is why magnets behave normally. That is why life is possible. The coherence gives us a usable reality. But underneath, the quantum web remains. Now, humans are learning to control it. Quantum computers use entangled qubits to perform calculations impossible for classical machines. Quantum cryptography uses entanglement to detect eavesdroppers. Quantum teleportation transfers states across space without moving matter. These are not science fiction. They exist. They work. They rely on non-locality. Einstein's spooky action is now engineering. What once looked like a flaw is now a feature. What once felt like a paradox is now a resource. This is how science progresses. By turning confusion into capability. By transforming mystery into machinery. And yet, even now, the deepest question remains. Why does the universe work this way? Why probabilities? Why entanglement? Why non-locality? Why mathematics fits reality so perfectly? No one knows. Every explanation ends somewhere. Every theory rests on axioms. At some point, physics must say, this is how it is. And that is not failure. It is the boundary of knowledge. What matters is not that we reached a final answer. What matters is that we learned how to ask better questions. Einstein did not lose. He forced physics to confront its foundations. He exposed hidden assumptions. He demanded clarity. Without his resistance, entanglement might have remained ignored. Without his skepticism, Bell might not have written his inequality. Without Bell, experiments might not have been done. Without experiments, we would still be guessing. Progress needs critics. It needs doubters. It needs people who refuse to be satisfied. In that sense, Einstein won, because he made understanding deeper. Today, when you hear that particles influence each other instantly across space, you are hearing about one of the most thoroughly tested facts in science. Not speculation, not theory. Evidence. You are hearing that reality is more connected than distance suggests. More unified than appearances imply. More subtle than intuition allows. And that realization changes how you see everything. You are not an isolated object moving through empty space. You are part of a network. Everything participates in everything else. So when you think about entanglement, you are not thinking about an exotic laboratory trick. You're thinking about the structure of reality, about how the universe keeps itself consistent, about how order emerges from probability, about how connection survives distance, and how human curiosity uncovered all of this using nothing but imagination, mathematics, and patience. That is the real story. Not just that quantum mechanics breaks classical rules, but that human minds learn to follow nature beyond intuition, beyond comfort, beyond common sense, into a domain where reality is stranger than any story, and still understandable. That is the legacy of Einstein. Not perfection, not certainty, but courage. The courage to question even the most successful theories. The courage to accept uncomfortable answers. The courage to follow truth wherever it leads. Even when it leads to a universe where distance is not what it seems, where certainty is optional, and where everything, in some quiet and invisible way, is connected.